Hi there, my name's Aaron Lanterman, and that is the Empire State Building, and I am on top of the rock. I recently went on a family trip to New York. I brought along this book called Collective Electrodynamics, Quantum Foundations of Electromagnetism by Carver Mead, to read on trains and planes. I really don't know what to make of this book. I could make a hat, or a brooch, or a pterodactyl. In the description for the book, it's promised that Carver Mead offers a radically new approach to the standard problems of electromagnetic theory. He describes a new way of doing electrodynamics, collective electrodynamics, that does not rely on Maxwell's equations, but rather uses the quantum nature of matter as its sole basis. Collective electrodynamics is a way of looking at how electrons interact based on experiments that tell us about the electrons directly. The results that Mead derives for standard electromagnetic problems are identical to those found in any text. Collective electrodynamics reveals, however, that quantities that we usually think of as being very different are, in fact, the same, that electromagnetic phenomena are simple and direct manifestations of quantum phenomena. Mead views his approach as a first step towards reformulating quantum concepts in a clear and comprehensible manner. Well, I'm not sure about the clear and comprehensible part. I found this book to be a real head-scratcher. Admittedly, electromagnetics is not my area. I'm a digital signal processing and analog circuits kind of guy. When I was an undergrad at Washington University in St. Louis many moons ago, I took the standard junior electromagnetics class. I was able to pattern match enough to turn the word problems into math, to apply Green's theorem and Stokes' theorem and stuff like that, but I never really developed an intuition for the subject. I was hoping that a lack of prior knowledge about classical or quantum electrodynamics might help me understand Carver's book, because I would be approaching it without any preconceived notions. Well, that didn't happen. Stephen Parrott was a professor at the University of Massachusetts, Boston, who, unlike me, very much is qualified to judge Carver's book. And Professor Parrott wrote an absolutely scathing review. He writes, "His naturally occurring one form is assumed to have the property that integrating it over a closed curve gives the change in phase of an electron wave function, which he never properly defines over the curve. Mead's proposed one form from quantum mechanics seems inherently unmeasurable, i.e. there is no way to determine it from experiment, or at least Mead doesn't propose any. Mead does not address the question of whether his change of phase in one form satisfies the retardation condition above. He just seems to assume it. In my opinion, the main problem with his argument is that his construction of his phase change one form is so vague, sloppy, and problematic that it is not even wrong." Ouch. But I'm reluctant to dismiss the whole thing because Carver Mead is an absolute legend in electrical and computer engineering. At a time when people assumed that supercomputers would always require CPUs built out of discrete logic chips with emitter-coupled logic, Carver Mead realized that a lot of things actually got better as you scaled the transistors to be smaller. Along with his colleague Lynn Conway, he established the kind of design rules that democratized modern digital VLSI design. And in the 1980s, he pioneered neuromorphic circuits using analog computation techniques. And he was the advisor of my colleague Jennifer Hassler, who I have co-authored several papers with. So if Carver Mead has some thoughts about physics, I'm inclined to pay attention. But as Angela Collier noted in one of her videos, even highly knowledgeable, highly experienced, highly accomplished people can sometimes go down the path of crackpottery. University of California Riverside math professor John Baez has a point system for determining crackpot theories in physics, number 8 of which is 5 points for each mention of Einstein, Hawkins, or Feynman. Now, Carver Mead mentions Feynman a lot, but Carver Mead gets special dispensation here because he was a professor at Caltech alongside Richard Feynman. Feynman actually joined Caltech as a professor the same year that Mead started as a freshman. Although I did read Collective Electrodynamics shortly after I watched Angela Collier's video on Richard Feynman, so the name dropping probably hit me a little different than it otherwise would. There's a fellow on Quora named Jim Weitzcarver who really liked the book. He wrote, "I contend that Collective Electrodynamics by Carver Mead is a book ahead of its time, flying in the face of the accepted physics paradigm, but providing a simpler and more understandable understanding of the deterministic quantum nature of our universe and how the illusion of electrodynamic forces is often, but not necessarily exhibited in the case of a large number of events." He shows how electromagnetism as taught in schools is wrong and is misleading our next generation of scientists. And while Mead wrote the book on semiconductor physics and is regarded to understand it better than anyone else and is considered a great educator, often compared with the likes of Feynman, his advice has largely gone unheeded. And let's see. Wow, this guy posts on Quora a lot. One thing that concerns me is that in the 25 years since Carver originally published this, it doesn't look like anyone's really followed up on it. I couldn't find any papers that cited it. I spent some time Googling around and I couldn't find any electrodynamics courses that seemed to use Carver's approach. But while I was doing that, I ran across this interesting post. The author said, "I'm always wary of some lone individual trying to redefine all of our understanding in a current field, as that's not really how science works. From what I gather, he's wrong because he's trying to make physics deterministic, when from what we gather in quantum physics it's kind of not, given the distribution of probabilities, not to mention the recent discovery of non-locality." One of the responders wrote, "There is vanishingly little being treated in that book. I so very much wanted to learn from that book because it aligned with my aesthetics, but it was so woefully underfleshed out that there it accomplished almost nothing compared to the grand goals it had set out to do. We cannot even judge whether it could have been good. The starting idea is okay, and so are the beginning parts of the text, but it isn't even complete enough for an undergrad dissertation." One nice thing about this YouTube channel having the size of audience that it does now is that for any topic I post about, there's somebody watching that's more knowledgeable about it than I am. So if you know the ways of electromagnetics and quantum physics, I would invite you to check out the book, and I would love to know your thoughts on it. You could leave a comment below. If you don't have means of acquiring the book, there is a paper online in the Proceedings of the National Academy of Sciences that you can read for free that appears to correspond directly to the first chapter of the book. I'll include a link to it in the description below.